Have you ever wondered what it would be like to receive a message from another star system? Right now, something remarkable is happening in the depths of space, something that's gently changing how we see ourselves in the universe. A visitor named 3I Atlas is racing through our solar system at 120,000 kilometers per hour, and it's carrying with it the most extraordinary library humanity has ever encountered. This isn't science fiction. Since September 2024, astronomers have been watching this interstellar traveler, only the third confirmed visitor from beyond our solar system, as it follows a graceful arc past the sun. But 3I Atlas isn't just passing through. It's teaching us in the most subtle and beautiful way possible. Every day, as sunlight warms its ancient surface, 3I Atlas releases molecules that formed in another star system millions of years ago. These particles carry the chemical signatures of distant worlds, like pages torn from a book written in a place we've never been. Scientists are reading these molecular stories with instruments so sensitive they can detect individual atoms floating in space. To understand what 3I Atlas is truly doing to humanity, we need to appreciate the incredible journey it has taken to reach us. This cosmic wanderer has been traveling through the void between stars for potentially millions of years, carrying with it a frozen record of the conditions where it was born. Imagine drifting through a darkness so complete that the nearest star appears as nothing more than a distant pinprick of light. The temperature in interstellar space hovers around minus 270 degrees Celsius, just 3 degrees above absolute zero. In this profound cold, molecules move so slowly they barely vibrate, preserving the original chemistry of 3I Atlas like a natural deep freezer that has operated for eons. During its long journey, 3I Atlas has been bombarded by cosmic rays, high-energy particles streaming from distant galaxies. These cosmic rays have slowly altered its surface, creating new chemical compounds and leaving radiation scars that tell the story of its passage through the galaxy. Each impact, each interaction with interstellar dust has added another chapter to its cosmic biography. As 3I Atlas approaches our sun, something magical begins to happen. The gentle warmth of solar radiation starts to sublimate the ices locked within its structure, creating a delicate coma of gas and dust around the nucleus. This isn't destruction, it's revelation. Each molecule that escapes carries information about the chemical processes that occurred in another star system. Astronomers use spectroscopy to decode these messages, splitting the light reflected and emitted by 3I Atlas into its component wavelengths. Think of it as creating a rainbow from the object's glow, but instead of simple colors, each wavelength reveals the presence of specific molecules. Water vapor shows up as distinct absorption lines, carbon monoxide creates its own signature, and organic compounds leave their unique fingerprints across the spectrum. What makes this process so extraordinary is that we're essentially performing archaeology on a cosmic scale. The molecules being released today formed around another star, possibly when our own solar system was still a swirling disk of dust and gas. 3I Atlas is giving us a direct sample of the raw materials that built worlds we'll never visit, delivered fresh to our telescopes after a journey that spans both vast distances and deep time. The arrival of 3I Atlas is fundamentally changing how we think about our place in the galaxy. For most of human history, we've imagined our solar system as an isolated island floating in the cosmic ocean. But interstellar visitors like 3I Atlas reveal that space isn't empty. It's filled with wandering messengers carrying news from distant shores. Consider this. Astronomers estimate that at any given moment, there could be dozens of interstellar objects passing through our solar system undetected. They move like ghosts through the darkness, too small and distant for our telescopes to spot. 3I Atlas represents just the tip of an enormous iceberg of interstellar material that flows constantly through our neighborhood. This revelation transforms our understanding of planetary formation and the distribution of life's building blocks throughout the galaxy. The organic molecules found on 3I Atlas, complex carbon compounds that could serve as precursors to biological processes, suggest that the chemistry necessary for life might be far more widespread than we previously imagined. We're not living in cosmic isolation, but rather in a galaxy where the ingredients for life are constantly being shuffled and redistributed like cards in an enormous cosmic deck. So what exactly is 3I Atlas doing to humanity? The answer lies not in dramatic transformation, but in the gentle accumulation of knowledge that reshapes our scientific worldview. Every measurement taken, every spectrum analyzed, every particle detected adds to our understanding of how planetary systems form and evolve throughout the galaxy. The data from 3I Atlas is helping astronomers refine their models of stellar nurseries, the vast clouds of gas and dust where new stars and planets are born. By comparing the chemical composition of our interstellar visitor with materials in our own solar system, scientists can identify which elements are common across different star-forming regions, and which are unique to specific cosmic environments. This knowledge has practical implications for the search for life beyond Earth. If 3I Atlas carries organic compounds that formed in another stellar system, it suggests that the basic chemistry of life might emerge naturally wherever conditions are right. Each interstellar object becomes a data point in the grand experiment of understanding whether life is a rare cosmic accident or an inevitable consequence of chemistry and time. Perhaps most remarkably, 3I Atlas functions as a time capsule, preserving conditions from the early stages of another planetary system's development. The ices and organic materials locked within its structure have remained largely unchanged during its million-year journey through the frozen vacuum of interstellar space. When our instruments analyze these ancient materials, we're essentially looking back in time to see what another star system was like when it was young. This is particularly valuable because our own solar system has undergone billions of years of evolution, mixing and processing its original materials through countless cycles of planetary formation, asteroid impacts, and gravitational interactions. 3I Atlas offers us a pristine sample of what stellar systems look like before this processing begins. It's like finding an unopened letter from the cosmic past, written in the universal language of chemistry and physics. As we decode its contents, we gain insights not just into distant worlds, but into the conditions that existed when our own Earth was forming, helping us understand the deep history of our cosmic home. As 3I Atlas glides through our solar system, it's performing an intricate gravitational ballet with the sun and planets. This cosmic choreography is so precise that astronomers can predict its path with extraordinary accuracy, calculating where it will be months or even years in advance. But this gravitational dance does more than just determine trajectory. It reveals the hidden mass and structure of our interstellar visitor. When 3I Atlas passes close to Jupiter, the giant planet's immense gravity tugs gently on the object, causing minute changes in its speed and direction. These tiny variations, measured to within centimeters per second, tell us about the internal structure of 3I Atlas. Is it a solid chunk of rock and ice, or does it have a more complex, layered composition? The gravitational fingerprints left by its passage provide answers that no telescope could reveal on its own. This gravitational interaction works both ways. While Jupiter influences 3E Atlas, the interstellar visitor also exerts its own infinitesimal pull on the giant planet. Though this effect is incredibly small, less than the gravitational influence of a car parked on Earth's surface, it represents a genuine exchange of momentum between our solar system and the wider galaxy, a physical connection that spans the void between stars. As weeks turn to months, 3I Atlas gradually reveals more of its secrets through the gentle process of outgassing. Different types of ice sublime at different rates as the object warms, creating a timeline of chemical revelations that unfolds like the chapters of a slowly opening book. First to evaporate are the most volatile compounds, carbon monoxide and nitrogen ices that turn to gas at temperatures still far below freezing. These create the initial wisps of the coma, the tenuous atmosphere that surrounds the nucleus. As 3I Atlas moves closer to the Sun, water ice begins to sublime, releasing not just pure water vapor, but also the organic molecules and dust particles that were frozen within the ice matrix. Each phase of this process teaches us something different about the conditions in the star system where 3I Atlas formed. The presence of carbon monoxide suggests formation in the cold outer regions of a planetary system, while complex organic molecules indicate that chemical processing was occurring even in those distant, frigid environments. It's as if we're watching the archaeological layers of an alien world being peeled away one molecule at a time. What makes the study of 3I Atlas truly remarkable is the unprecedented level of international cooperation it has inspired. Telescopes scattered across 6 continents track its progress, sharing data in real time through secure networks that span the globe. This collaborative effort represents one of the most coordinated scientific observations in human history. Ground-based observatories in Chile's Atacama Desert work in perfect synchronization with radio telescopes in Australia, while infrared detectors in Hawaii complement ultraviolet observations from space-based platforms. Each instrument contributes a different piece of the puzzle, creating a comprehensive portrait of our interstellar visitor that no single telescope could achieve alone. The timing of these observations requires precision choreography. As Earth rotates, different telescopes come online to continue the vigil, ensuring that 3I Atlas is never out of sight for more than a few hours. This continuous monitoring has revealed subtle changes in the object's brightness and spectral signature that occur over time frames as short as minutes, variations that might hold clues to its internal structure and rotation. Deep within the spectral data collected from 3I Atlas lies perhaps the most intriguing discovery of all, the presence of complex organic molecules that form the building blocks of life as we know it. These aren't simple compounds, but rather intricate molecular structures that require specific conditions to form and survive. Among the organic signatures detected are methanol, formaldehyde, and hydrogen cyanide, molecules that might sound dangerous in earthly contexts, but represent crucial steps in the cosmic chemistry that leads to biological complexity. More remarkably, astronomers have identified traces of amino acid precursors, the molecular foundations from which proteins are built in living organisms. The presence of these compounds suggests that 3I Atlas formed in an environment rich with the raw materials for life. This doesn't mean our visitor carries living organisms. The harsh conditions of its million-year journey would have sterilized any biological material. But it does indicate that the chemistry necessary for life exists far beyond our solar system, scattered throughout the galaxy like seeds waiting for the right conditions to flourish. One of the most revealing aspects of 3I Atlas comes from studying the isotopic ratios within its materials. Isotopes are different versions of the same element, with varying numbers of neutrons in their nuclei. These ratios act like cosmic fingerprints, revealing the specific stellar environment where the materials formed. The oxygen isotopes in the water vapor released by 3I Atlas show a distinctly different signature from those found in our solar system's comets. This difference tells us that our visitor formed around a star with different characteristics from our Sun, perhaps a cooler, redder star, or one with a different metallicity. Each isotopic measurement adds another piece to the puzzle of 3I Atlas's cosmic origins. Particularly intriguing are the nitrogen isotope ratios, which suggest formation in a region of space enriched by the explosive deaths of massive stars. Supernovae scatter heavy elements throughout the galaxy, and the isotopic signatures they create serve as timestamps, telling us when and where in galactic history these stellar explosions occurred. 3I Atlas carries within its ices the atomic fingerprints of stars that died millions of years before our own Sun was born. As months pass and 3I Atlas continues its journey through our solar system, its most profound effect on humanity becomes clear. This interstellar messenger is quietly transforming our perspective on our place in the universe, not through dramatic revelation, but through the steady accumulation of knowledge that reshapes how we see ourselves. Before the arrival of interstellar visitors like Oumuamua, Borisov, and now 3I Atlas, we could only speculate about conditions in other stellar systems based on distant observations and theoretical models. Now we have actual samples, albeit tiny ones, of the materials that built worlds around other stars. This represents a fundamental shift from astronomy to what we might call hands-on cosmology. The psychological impact of this shift is subtle but profound. We're no longer isolated observers peering at distant lights in the sky, but participants in a galactic ecosystem where materials and potentially life itself flow between stellar systems like nutrients circulating through a vast cosmic organism. 3I Atlas reminds us that we are connected to the wider universe in ways both physical and chemical, part of an ongoing story that spans billions of years and countless worlds. The trajectory of 3I Atlas through our solar system follows mathematical principles that have remained unchanged since the formation of the galaxy. Its hyperbolic orbit, a path that curves around the Sun but never closes into a repeating ellipse, demonstrates the precise balance between gravitational attraction and kinetic energy that governs all motion in space. What makes this orbital mechanics particularly fascinating is how it reveals the hidden influence of dark matter on galactic structure. The velocity and direction of 3I Atlas as it entered our solar system carry information about the gravitational environment it encountered during its long journey between stars. By analyzing these parameters, astronomers can map the distribution of invisible matter that shapes the flow of objects through our corner of the Milky Way. The precision required to track 3I Atlas involves calculations that push the boundaries of computational astronomy. Every gravitational tug from Jupiter, every minute force from solar radiation pressure, every tiny change in the object's mass as it loses material through outgassing, all of these factors must be accounted for to predict its future position accurately. The result is a mathematical portrait of cosmic forces acting across scales from atomic to galactic. As 3I Atlas follows its predetermined path through the inner solar system, its changing distance from the Sun creates distinct seasons of scientific discovery. During its approach, increasing solar heating triggers more vigorous outgassing, revealing layers of material that have remained frozen for millions of years. The peak activity occurs during perihelion, the point of closest approach to the Sun, when surface temperatures rise enough to activate even the most stubborn ices. This is when 3I Atlas becomes most generous with its secrets, releasing clouds of vapor that expand and dissipate in the solar wind like cosmic morning mist. Spectroscopic observations during this period capture the full chemical complexity of our interstellar visitor. As 3I Atlas begins its journey back toward the outer reaches of the solar system, the opportunity for detailed study gradually diminishes. The object grows fainter and more distant with each passing day. Its outgassing slows, and eventually it will fade beyond the detection limits of even our most powerful telescopes. This natural rhythm of revelation and concealment adds urgency to every observation, making each data point precious. While 3I Atlas itself will eventually disappear into the cosmic darkness from which it came, it leaves behind something invaluable, samples of dust and gas that have been captured by spacecraft and research instruments throughout the solar system. These microscopic remnants represent the first direct samples of interstellar material that humans have ever possessed. Laboratory analysis of these particles reveals details invisible to even the most sophisticated telescopes. Under electron microscopes, individual dust grains show the scars of cosmic ray bombardment accumulated over millions of years. Mass spectrometers identify trace elements present in concentrations too small to detect remotely, but rich with information about stellar nucleosynthesis processes. The isotopic composition of these samples will be studied for decades, each measurement adding to our understanding of galactic chemical evolution. Some particles contain mineral structures that could only have formed under specific temperature and pressure conditions, providing clues about the environment where 3I Atlas originated. Others show evidence of alteration by interstellar radiation, documenting the slow changes that occur during the long journey between stars. Hidden within the structure of 3I Atlas lies one of the most fascinating aspects of its cosmic journey: magnetic signatures that tell the story of the stellar environment where it formed. Like a cosmic recording device, the minerals within our interstellar visitor have preserved the magnetic field patterns they experienced during their formation billions of years ago. When 3I Atlas first condensed from the primordial disk surrounding its parent star, tiny iron-bearing particles within its structure aligned themselves with the magnetic field lines of that ancient solar system. These microscopic compasses have remained frozen in their original orientations throughout the long journey between stars, creating a magnetic fossil record that scientists can now decode using sophisticated magnetometers aboard space-based observatories. The magnetic data reveals something remarkable. The star system, where 3I Atlas formed, possessed a magnetic field roughly twice as strong as our Sun's current field. This suggests formation around a younger, more active star, one that was still in the vigorous phase of stellar evolution when powerful magnetic storms regularly swept through its planetary system. These ancient magnetic tempests may have played a crucial role in shaping the chemistry and structure of the materials that eventually became our cosmic visitor. Even more intriguing are the magnetic reversals recorded in different layers of 3I Atlas's structure. Just as Earth's magnetic field has flipped its polarity numerous times throughout geological history, the magnetic field of the distant star system where our visitor formed also underwent periodic reversals. By studying these magnetic layers, astronomers can reconstruct the timeline of stellar evolution in a solar system that existed when the universe was significantly younger than it is today. The preservation of these ancient magnetic signatures required extraordinarily stable conditions during 3I Atlas's interstellar voyage. The near-perfect vacuum of space and temperatures hovering just above absolute zero created an ideal environment for magnetic preservation. It's as if the cosmos provided a perfect storage facility for these precious records, delivering them to us unchanged after a journey spanning millions of years and countless light-years of distance. As 3I Atlas continues its graceful passage through our solar system, the molecules escaping from its surface perform an intricate dance governed by the laws of physics and chemistry. This isn't random chaos, but rather a precisely choreographed performance that reveals the internal structure and composition of our interstellar visitor with each passing day. The initial release of gases follows predictable patterns based on molecular weight and volatility. Lighter molecules like hydrogen and helium, if present, escape first and most easily, followed by slightly heavier compounds like water vapor and carbon dioxide. The heavier organic molecules require more energy to break free from the surface, creating a natural timeline of chemical revelation that unfolds as solar heating gradually penetrates deeper into the object's interior. But the molecular escape isn't uniform across the surface of 3I Atlas. Different regions release different combinations of compounds, suggesting that our visitor has a heterogeneous structure. Some areas rich in water ice, others dominated by carbon-based materials, still others containing rocky minerals that formed under high-temperature conditions. This patchy composition tells us that 3I Atlas likely formed through the gradual accumulation of materials from different regions of its parent star system's disk. The solar wind, a constant stream of charged particles flowing outward from the sun, interacts with these escaping molecules in fascinating ways. The charged particles act like invisible sculptors, shaping the expanding cloud of gas and dust into elongated structures that can extend millions of kilometers behind 3I Atlas. These formations, visible only through specialized instruments, create ephemeral artworks in space that exist for weeks or months before dissipating into the cosmic background. Most remarkably, some of the organic molecules released by 3I Atlas undergo chemical reactions as they encounter solar radiation. Ultraviolet light from the sun breaks apart complex compounds and allows them to recombine in new ways, essentially performing chemistry experiments in the vacuum of space. These reactions create molecular species that may never have existed before, adding new chapters to the chemical story of our interstellar visitor, even as it shares the secrets of its ancient origins. The gravitational influence of 3I Atlas on our solar system creates subtle harmonies that resonate through space like notes in a cosmic symphony. While individually tiny, these gravitational effects combine and interact in ways that reveal hidden aspects of both our visitor and the solar system it's passing through. Every planet and moon in our solar system exerts its own gravitational pull on 3I Atlas, creating a complex web of forces that must be carefully calculated to predict the object's future trajectory. But this isn't a one-way interaction. Newton's third law ensures that 3I Atlas tugs back on each celestial body with equal and opposite force, creating microscopic but measurable changes in planetary orbits that persist long after our visitor has departed. These gravitational perturbations are so small that they require the most precise measurement techniques available to modern astronomy. Laser interferometry systems can detect changes in planetary positions equivalent to the width of a single atom, revealing the subtle gravitational fingerprints left by 3I Atlas's passage. The data contributes to our understanding of celestial mechanics and helps refine the mathematical models we use to predict the motions of objects throughout the solar system. Perhaps most fascinating is how the gravitational field of 3I Atlas interacts with the tidal forces generated by Jupiter and Saturn. As our interstellar visitor passes through regions where these giant planets' gravitational influences overlap, it experiences complex tidal stresses that cause minute changes in its rotation rate and internal structure. These effects are so subtle that they're barely detectable, but they provide valuable information about the internal composition and structural integrity of our cosmic guest. The gravitational resonances created by 3I Atlas's passage also affect the orbits of smaller objects in the outer solar system, asteroids, comets, and debris from the Kuiper Belt. Some of these tiny bodies experience slight changes in their trajectories that will influence their paths for centuries to come. In a very real sense, 3I Atlas is leaving a permanent gravitational signature on our solar system, a reminder of its brief but significant visit that will persist long after the object itself has disappeared into the darkness between stars. Within the microscopic structure of 3I Atlas lies perhaps the most extraordinary library ever discovered. Crystalline formations that have preserved atomic-level information about stellar processes that occurred billions of years ago. These mineral crystals, no larger than grains of sand, contain within their lattice structures a detailed record of the nuclear fusion reactions, stellar winds, and supernova explosions that shaped the galaxy during its youth. When high-energy cosmic rays bombarded 3I Atlas during its long interstellar journey, they occasionally struck atomic nuclei within these crystals, creating distinctive damage tracks that can be read like microscopic fossil records. Each track tells the story of a single high-energy particle, perhaps a proton accelerated by a distant pulsar, or a heavy nucleus ejected from a dying star millions of years ago. By studying the density and orientation of these tracks, Scientists can reconstruct the radiation environment that 3I Atlas encountered during different phases of its journey. The crystal structures themselves reveal the temperature and pressure conditions that existed when they formed. Some crystals show evidence of formation in the frigid outer regions of a protoplanetary disk, where temperatures barely rose above absolute zero. Others contain mineral phases that could only have formed at much higher temperatures, suggesting that 3I Atlas incorporates materials from multiple zones within its birth system, perhaps fragments blasted from the inner system by stellar winds or gravitational perturbations. Most remarkably, some crystals within 3I Atlas contain trapped pockets of ancient gases, actual samples of the stellar atmosphere that existed around its parent star billions of years ago. These microscopic gas bubbles preserve the isotopic composition and chemical makeup of stellar material from an era when the galaxy was fundamentally different from what we see today. The abundance ratios of different elements tell us about the nuclear processes occurring within that ancient star, providing direct evidence of stellar evolution in the early universe. The preservation of these crystalline archives required extraordinary circumstances. The materials had to form under specific conditions, survive ejection from their birth system, endure millions of years of cosmic ray bombardment, and finally arrive in our solar system with their delicate structures intact. The fact that we can now study these ancient records represents one of the most remarkable achievements in the history of astronomy. The ability to hold in our hands samples of matter that witness the birth and death of stars in distant corners of space and time. Deep within the atomic structure of 3I Atlas lies evidence of one of the universe's most fundamental processes, the creation of heavy elements within the cores of ancient stars. Every atom heavier than hydrogen and helium was forged in the nuclear furnaces of stellar interiors, or in the explosive deaths of massive stars. And 3I Atlas carries within its structure the quantum signatures of these primordial creation events. The isotope ratios found in our interstellar visitor tell a detailed story of stellar nucleosynthesis that occurred billions of years ago. Elements like iron, nickel, and cobalt show the distinctive signatures of formation within the cores of stars at least 8 times more massive than our Sun. These stellar giants burned through their nuclear fuel in just millions of years before exploding as supernovae, scattering their newly forged elements throughout the surrounding space. But 3I Atlas also contains evidence of slower, more patient processes of element creation. The presence of elements like strontium, barium, and lead points to formation through the S process, slow neutron capture that occurs over thousands of years within the cores of aging red giant stars. These stellar ancestors gradually built up heavy elements one neutron at a time, like cosmic alchemists patiently transmuting lighter elements into heavier ones through the gentle application of neutron flux. Perhaps most intriguing are the traces of elements that could only have formed in the most violent events in the universe: neutron-star mergers. When two ultra-dense stellar remnants spiral into each other and collide, they create conditions of temperature and density that briefly exceed those found in stellar cores. These cosmic catastrophes forge the heaviest elements in the periodic table: gold, platinum, uranium, in explosions so energetic they create ripples in space-time itself. The quantum signatures preserved in 3I Atlas provide a direct connection to these ancient cosmic events. By studying the precise isotopic composition of these heavy elements, astronomers can estimate when and where these stellar explosions occurred relative to the formation of our interstellar visitor. It's as if 3I Atlas carries within its structure a detailed timeline of stellar death and rebirth, a quantum fossil record of the violent processes that enriched the galaxy with the elements necessary for rocky planets and ultimately life itself. The temperature history encoded within 3I Atlas tells a fascinating story of ancient stellar climates and the thermal evolution of planetary systems. Like tree rings recording annual variations in weather, the layered structure of our interstellar visitor preserves a record of temperature fluctuations that occurred during its formation billions of years ago. Detailed analysis of mineral phases within 3I Atlas reveals evidence of episodic heating events that occurred during its early history. Some materials show signs of having been briefly heated to temperatures of several hundred degrees Celsius before rapidly cooling back to the frigid conditions of the outer solar system. These thermal signatures likely record close encounters with the hot inner regions of its birth system, perhaps during periods when gravitational perturbations from forming planets scattered materials throughout the developing stellar system. The thermal history also reveals information about the evolution of the star around which 3I Atlas formed. During the early phases of stellar development, young stars experience periods of intense activity, massive flares, powerful stellar winds, and dramatic variations in luminosity. These events would have created waves of thermal energy that propagated outward through the surrounding disk of planetary materials, leaving their signatures in the crystal structures that were forming at the time. Most remarkably, the thermal record preserved in 3I Atlas shows evidence of periodic heating cycles that may have been driven by the orbital dynamics of forming planets. As large planetary bodies migrated through the early stellar system, their gravitational influence would have stirred up the surrounding disk, creating friction and heating events that left distinctive thermal signatures in the materials that eventually became our cosmic visitor. The slow cooling history that followed these early heating events tells us about the gradual thermal evolution of the outer regions of the stellar system. As the central star settled into its stable main sequence phase and the surrounding disk dissipated, temperatures dropped steadily toward the near absolute zero conditions of interstellar space. This cooling process locked the thermal signatures into the crystal structure of 3I Atlas, preserving them like memories frozen in time until their arrival in our solar system billions of years later. Perhaps no aspect of 3I Atlas has captured the imagination of scientists more than the complex organic chemistry preserved within its ancient structure. As our interstellar visitor releases its molecular inventory through gentle outgassing, we're witnessing the unveiling of a prebiotic laboratory that has been conducting chemical experiments in slow motion for millions of years during its journey between stars. This cosmic chemistry set contains molecular recipes that were written in the cold darkness of space, using ingredients that formed around a distant star billions of years ago. The organic compounds detected in the spectral signatures of 3I Atlas represent far more than simple carbon-based molecules. They constitute a sophisticated chemical library that includes amino acid precursors nucleotide bases, complex hydrocarbon chains, and even structures that resemble the basic components of cell membranes. What makes these discoveries so extraordinary is that these compounds formed and survived under conditions completely different from those found anywhere in our solar system, suggesting that the chemistry of life may be far more universal and resilient than we previously imagined. Among the most intriguing organic signatures are complex aromatic compounds, ring-shaped molecular structures that serve as the backbone for many biological molecules. These compounds, including polycyclic aromatic hydrocarbons, nitrogen-bearing heterocycles, and sulfur-containing thiophenies, demonstrate a level of chemical sophistication that indicates active organic synthesis occurred in the stellar environment where 3I Atlas formed. The presence of these molecules suggests that the raw materials for life's chemistry are not unique to Earth-like environments, but may be common throughout the galaxy, arising naturally wherever carbon, hydrogen, oxygen, and nitrogen are brought together under appropriate conditions. The isotopic composition of the carbon and nitrogen within these organic compounds provides additional clues about their stellar origins and formation pathways. The carbon isotope ratios differ significantly from those found in terrestrial organic matter, indicating formation under different stellar conditions, perhaps around a star with different nuclear burning processes, or in a region of space enriched by different types of supernovae. These isotopic fingerprints allow scientists to trace the genealogy of organic molecules back to their stellar sources, creating a family tree of cosmic chemistry that spans billions of years and countless light-years of space. Particularly fascinating is the discovery of what appear to be membrane-forming compounds within 3I Atlas, lipid-like molecules that have the potential to self-organize into cell-like structures under appropriate conditions. Laboratory experiments conducted with similar compounds extracted from carbonaceous meteorites have demonstrated that these cosmic lipids can indeed form stable membrane vesicles when placed in liquid water, creating hollow spheres that resemble primitive cell membranes. While these compounds are not alive in any biological sense, their presence demonstrates that the self-assembly processes fundamental to life's organization can occur spontaneously in cosmic environments, suggesting that the transition from chemistry to biology may be more common than previously thought. The preservation of these delicate organic compounds throughout 3I Atlas's million-year interstellar journey speaks to the remarkable stability of complex chemistry in the deep cold of space. Temperatures just a few degrees above absolute zero essentially freeze all chemical reactions, creating a perfect preservation environment for even the most fragile molecular structures. The cosmic void has served as the ultimate laboratory freezer, maintaining these ancient organic compounds in pristine condition while protecting them from the destructive effects of liquid water, atmospheric oxygen, and biological processes that would rapidly decompose them on Earth. The study of these organic compounds is revolutionizing our understanding of astrobiology, the study of life in the universe. If complex organic chemistry can survive and even slowly evolve during interstellar transit, it suggests that the seeds of life may be constantly flowing between stellar systems, carried by objects like 3I Atlas in a process that scientists call panspermia. This concept proposes that life's building blocks are distributed throughout the galaxy by interstellar travelers, potentially seeding new worlds with the molecular tools necessary for biological evolution whenever they encounter environments with liquid water and appropriate energy sources. The implications extend beyond simple molecule delivery. Some researchers speculate that the organic compounds in 3I Atlas may have undergone slow chemical evolution during their interstellar journey, driven by cosmic ray bombardment and quantum mechanical processes that can occur even at extremely low temperatures. This cosmic chemistry could produce molecular innovations, new types of organic compounds that might never form under terrestrial conditions, expanding the toolkit of prebiotic chemistry beyond what we observe in Earth's biosphere. As 3I Atlas continues its stately procession through our solar system, it serves as more than just a passive object of study. It functions as an active transmitter and receiver of electromagnetic signals that carry information about the cosmic environment through which it has traveled. The electromagnetic spectrum emanating from our interstellar visitor tells a complex story of galactic evolution, stellar formation cycles, and the invisible forces that shape the universe on scales ranging from atomic to galactic. The radio emissions detected from 3I Atlas are particularly intriguing, as they appear to be generated by multiple physical processes operating simultaneously. The primary mechanism involves the interaction of cosmic ray particles with the object's magnetic field and surface materials, creating synchrotron radiation as charged particles spiral along magnetic field lines. These radio signals carry encoded information about the interstellar magnetic field environment that 3I Atlas encountered during its long journey, providing astronomers with direct measurements of magnetic field strengths, orientations, and turbulent structures in regions of space that are otherwise impossible to study directly. The magnetic field data reveals a complex tapestry of structures threading through the local galactic neighborhood. These fields, shaped by stellar winds, supernova explosions, and the differential rotation of the galaxy itself, create invisible highways that guide the motion of charged particles and influence the formation of new stars. The radio emissions from 3I Atlas essentially provide us with a map of these magnetic highways, showing how they connect different regions of the galaxy and revealing the dynamic processes that have shaped our cosmic environment over millions of years. Infrared observations of 3I Atlas reveal thermal signatures that change subtly as different regions of the object rotate into and out of view. These thermal variations indicate that our cosmic visitor has a remarkably heterogeneous surface composition, with some areas retaining heat more effectively than others due to differences in thermal conductivity, surface roughness, and chemical composition. The thermal mapping reveals geological-like features that may record impact events from interstellar dust grains, internal heating episodes caused by radioactive decay, or compositional variations that occurred during the object's formation in its distant birth system. The most intriguing thermal features appear to be organized in patterns that suggest large-scale structure within 3I Atlas. Some regions show evidence of layered compositions, possibly indicating that our visitor formed through the gradual accretion of materials from different zones within its parent stellar system. Other areas display thermal anomalies that may indicate the presence of subsurface voids, regions of different density, or concentrations of radioactive materials that continue to generate small amounts of heat even after billions of years. The object's interaction with the solar wind creates additional electromagnetic phenomena that provide insights into both 3I Atlas's properties and the nature of space plasma dynamics. As the charged particle stream from the Sun encounters the expanding coma of gas and dust around our visitor, it creates bow shock structures, magnetic field reconnection events, and plasma instabilities that can be detected by sensitive magnetometers and plasma detectors aboard spacecraft throughout the solar system. These interactions essentially turn 3I Atlas into a moving laboratory for studying fundamental plasma physics processes that occur throughout the universe. Ultraviolet observations reveal the fluorescence and phosphorescence of atmospheric gases around 3I Atlas as solar radiation ionizes and excites molecules in the expanding coma. The resulting emission lines provide detailed information about the chemical composition, temperature, and density structure within the object's temporary atmosphere. Different molecules glow at characteristic wavelengths when excited by solar photons, creating a spectroscopic fingerprint that reveals not only what compounds are present, but also their three-dimensional distribution around the nucleus and the energy transfer processes occurring within the coma. Perhaps most remarkably, 3I Atlas appears to be generating weak but detectable X-ray emissions through multiple mechanisms. The primary source appears to be charge exchange reactions between highly ionized atoms in the solar wind and neutral atoms in the object's coma, a process that strips electrons from neutral atoms and causes them to emit X-rays as the electrons cascade to lower energy levels. Additional X-ray emission may come from the fluorescence of heavy elements within the object's structure when they are struck by cosmic ray particles, creating a faint but persistent X-ray glow that provides information about the composition and internal structure of our interstellar visitor. The electromagnetic portrait of 3I Atlas is constantly evolving as the object moves through different regions of the solar system and encounters varying intensities of solar radiation, magnetic field strengths, and plasma conditions. This dynamic behavior allows astronomers to study how the object responds to changing environmental conditions, providing insights into its internal structure, surface properties, and the physical processes governing its interaction with the surrounding space environment. One of the most subtle yet profound effects of 3I Atlas's presence in our solar system involves its gravitational influence on the fabric of space-time itself, creating a cosmic choreography that operates according to the elegant mathematics of Einstein's general relativity. While the object's mass is relatively small compared to planets or moons, it nonetheless creates measurable distortions in the geometry of space and time that can be detected using the most precise instruments available to modern astronomy, revealing the fundamental interconnectedness of matter, energy, and the structure of the universe. Einstein's theory tells us that mass and energy curve space-time, and even an object as small as 3I Atlas creates tiny ripples in this cosmic fabric that propagate outward at the speed of light. These gravitational effects, while incredibly weak compared to those generated by planets or stars, can be measured using laser interferometry techniques similar to those employed by the LIGO and Virgo gravitational wave detectors. The passage of 3I Atlas through our solar system creates minute changes in the distance between widely separated points in space, alterations so small they amount to fractions of the width of a proton, but nonetheless detectable with sufficiently sensitive equipment operated over extended periods. The gravitational field of 3I Atlas also acts as a weak gravitational lens, slightly bending the path of light from distant stars as their photons pass through the curved spacetime in the vicinity of our cosmic visitor. This gravitational lensing effect is extraordinarily subtle. The deflection of starlight amounts to mere micro-arc seconds, angles so small they would be equivalent to resolving a coin on the moon's surface from Earth, but it can be measured using advanced astrometric techniques that track stellar positions with unprecedented precision over months of careful observation. These lensing observations provide an independent method for determining the mass distribution and internal structure of 3I Atlas, complementing other measurement techniques and offering insights into whether our visitor is a solid monolithic object or a more loosely bound collection of smaller fragments held together by weak gravitational and cohesive forces. The precise shape of the lensing signature reveals information about mass concentrations within the object, potentially identifying dense rocky components, hollow regions, or variations in composition that affect the local gravitational field. As 3I Atlas moves through the solar system's complex gravitational environment, it experiences tidal forces generated by the sun and planets that create minute deformations in the object's shape and internal structure. These forces, similar to those that raise ocean tides on Earth but operating on much smaller scales, can be detected through careful monitoring of the object's rotational dynamics, light curve variations, and the subtle changes in its gravitational field as different regions of varying density rotate into and out of alignment with our observation points. The tidal response of 3I Atlas reveals crucial information about its internal cohesion and structural properties. A solid, rocky object would resist tidal deformation much more effectively than a loosely bound collection of smaller fragments, creating distinctly different signatures in the observational data. By analyzing these tidal signatures, scientists can essentially perform a kind of gravitational medical imaging on our cosmic visitor, revealing its internal anatomy without ever physically touching its surface. The gravitational interactions between 3I Atlas and other objects in the solar system also provide valuable opportunities for testing the accuracy of Einstein's equations under conditions that are impossible to replicate in terrestrial laboratories. By precisely tracking the object's trajectory and comparing it to theoretical predictions based on general relativity, astronomers can search for subtle deviations that might indicate the presence of new physics beyond our current theoretical framework, perhaps modifications to gravity that become apparent only over cosmic distances, or in the presence of exotic forms of matter. Perhaps most intriguingly, the gravitational field of 3I Atlas interacts with the quantum vacuum of space in ways that may produce detectable effects at the intersection of gravitational physics and quantum mechanics. According to quantum field theory, even apparently empty space is filled with virtual particle pairs that constantly appear and disappear on timescales too brief to observe directly. The gravitational field of our cosmic visitor may influence these quantum fluctuations in subtle ways, potentially creating minute changes in the electromagnetic properties of the vacuum that could be detected using extremely sensitive instruments capable of measuring field variations smaller than those generated by the thermal motion of atoms. The gravitational effects of 3I Atlas also extend to its influence on the trajectories of smaller objects throughout the solar system. Dust particles, micrometeorites, and even spacecraft experience tiny gravitational tugs as our interstellar visitor passes through their vicinity. While these effects are individually negligible, their cumulative influence over time contributes to the ongoing gravitational evolution of the solar system, slightly altering the orbits of countless small bodies in ways that will persist long after 3I Atlas itself has departed for the interstellar void. As 3I Atlas continues its elegant passage through the inner solar system, it creates one of the most beautiful and scientifically revealing phenomena in astronomy, the formation and evolution of its dust tail and surrounding coma. This isn't merely the simple shedding of particles, but rather a complex hydrodynamic symphony that unfolds across millions of kilometers of space, governed by the intricate interplay between solar radiation pressure, gravitational forces, electromagnetic fields, and plasma dynamics that create a constantly evolving masterpiece of cosmic choreography. The dust particles released from 3I Atlas span an extraordinary range of sizes and compositions, from individual molecules and atomic clusters smaller than viruses to larger fragments comparable to sand grains and small pebbles. Each size population behaves differently in the solar environment, creating a natural sorting mechanism that spreads the particles across vast regions of space according to their physical properties. This cosmic particle accelerator reveals the internal structure and composition of our interstellar visitor with each passing day as different materials are preferentially released from various depths and regions within the object. The smallest particles, consisting of individual molecules and tiny clusters of atoms, are quickly accelerated away from the sun by radiation pressure, the gentle but persistent push of photons that creates a cosmic wind powerful enough to overcome the sun's gravitational attraction for such minute particles. These molecular-scale fragments travel at speeds exceeding 100 kilometers per second, carrying with them the chemical fingerprints of 3I Atlas's interior and creating an expanding cloud of interstellar material that will eventually merge with the interplanetary medium. Larger dust grains follow more complex trajectories that depend on their size, density, shape, and composition in ways that reveal the heterogeneous nature of our cosmic visitor. These particles experience a delicate balance between solar gravity trying to pull them toward the sun and radiation pressure pushing them away, with the balance point depending critically on the particle's ability to absorb and scatter sunlight. Rocky particles rich in silicate minerals behave differently from organic dust grains, while metallic fragments follow yet another set of dynamical rules, creating distinct streams and structures within the expanding dust cloud. The result is a gossamer tail that extends millions of kilometers behind 3I Atlas, constantly changing shape and brightness as our cosmic visitor moves through its orbit and experiences varying levels of solar heating and illumination. The tail structure reveals detailed information about the size distribution, composition, and release mechanisms of particles being expelled from the nucleus, essentially turning our interstellar visitor into a natural laboratory for studying the physics of dust dynamics in space environments. The interaction between dust particles and the solar wind creates additional layers of complexity in this cosmic choreography that would challenge the most sophisticated computer simulations. When high-energy charged particles from the sun collide with dust grains, they can alter the particle's electrical charge, surface chemistry, and even internal structure through a process called sputtering that gradually erodes the grain surfaces and releases atoms and small molecules back into the surrounding space. Some particles become negatively charged and are deflected by the solar wind's embedded magnetic field, while others acquire positive charges that cause them to spiral along magnetic field lines in complex helical trajectories. These electromagnetic effects create intricate substructures within the tail that can be observed using specialized polarimetric instruments sensitive to the way dust particles scatter and polarize sunlight. The polarization signatures reveal information about particle shape, composition, and size distribution that cannot be obtained through any other observational technique, providing insights into the formation processes and evolutionary history of the materials that make up 3I Atlas. The dust tail also serves as a sensitive probe of the solar wind environment itself, acting like a vast array of test particles that sample plasma conditions throughout a large volume of space. As particles move through regions with different magnetic field strengths, plasma densities, and turbulence levels, their trajectories change in ways that reflect the local conditions. By carefully tracking the motion of individual dust streams using advanced image processing techniques, astronomers can map the three-dimensional structure of the solar wind and its embedded magnetic field with unprecedented spatial and temporal resolution. Perhaps most remarkably, some of the dust particles released by 3I Atlas will eventually reach Earth's atmosphere, where they will create brief but brilliant meteor streaks as they burn up during atmospheric entry at speeds exceeding 60 kilometers per second. These cosmic visitors will carry with them the isotopic and chemical fingerprints of their interstellar origin, adding new signatures to Earth's atmospheric composition that may be detectable in ice cores, atmospheric samples, and even the cosmic dust that continuously falls on our planet's surface. In this way, 3I Atlas will leave a permanent chemical mark on Earth's inventory, a subtle but measurable reminder of our connection to the broader galactic community. The study of dust dynamics around 3I Atlas is also providing revolutionary new insights into the formation and evolution of planetary systems throughout the galaxy. The processes we observe occurring around our interstellar visitor, particle sorting by radiation pressure, electromagnetic acceleration and deflection, plasma dust interactions, and the gradual erosion of solid materials by energetic particles, are the same fundamental mechanisms that operated during the early stages of planetary formation in our own solar system and continue to shape the evolution of debris disks around young stars throughout the galaxy. The study of 3I Atlas presents us with one of the most fascinating paradoxes in modern astronomy, the ability to simultaneously look backward and forward in time through the lens of a single cosmic object, creating a temporal bridge that spans billions of years and connects the ancient history of our galaxy with potential futures that await our own solar system. This interstellar visitor serves as both a perfectly preserved time capsule from the ancient past and a prophetic glimpse of processes that will shape the evolution of planetary systems throughout the galaxy for eons to come. The materials composing 3I Atlas formed during a fundamentally different epoch in galactic history, when the universe was significantly younger, and the Milky Way bore little resemblance to the mature spiral galaxy we observe today. During that ancient era, stellar formation rates were dramatically higher, creating a cosmic environment rich with the energetic phenomena associated with young, massive stars. Powerful stellar winds, frequent supernova explosions, and intense radiation fields that would have dominated the interstellar medium in ways that are difficult to imagine from our current vantage point in cosmic history. The galaxy also contained fewer heavy elements during the formation period of 3I Atlas's constituent materials. The first generations of stars had only recently begun the process of nuclear fusion that creates elements heavier than hydrogen and helium, meaning that the raw materials available for planetary formation were fundamentally different from those that existed when our own solar system condensed from the interstellar medium 4.5 billion years ago. By analyzing the isotopic signatures and elemental abundances preserved within our cosmic visitor, we're essentially conducting archaeology on a galactic scale, uncovering direct evidence of stellar nucleosynthesis processes and chemical evolution pathways that operated when the galaxy was still in its formative stages. Yet 3I Atlas also serves as a remarkably accurate preview of Earth's distant future, carrying within its structure examples of the kinds of materials that will eventually escape from our own solar system as the Sun evolves through its inevitable stellar life cycle. When our star exhausts the hydrogen fuel in its core and begins to expand into a red giant approximately 5 billion years from now, the increased luminosity and stellar wind will gradually strip away the atmospheres of the terrestrial planets, evaporate Earth's oceans, and eventually eject significant quantities of formerly terrestrial material into interstellar space. The organic compounds and water ice that make up significant portions of 3I Atlas represent exactly the kinds of materials that will carry the chemical legacy of Earth's biosphere into the cosmic void. The amino acids, nucleotide bases, and complex carbon compounds that currently define our planet's living systems will be preserved in the deep cold of interstellar space, potentially beginning their own million-year journey toward distant star systems where they might contribute to the emergence of new forms of life on alien worlds. This temporal duality creates a unique perspective on cosmic evolution that spans geological ages and connects processes operating on vastly different timescales. The chemical reactions we observe occurring as 3I Atlas outgases in response to solar heating mirror the same fundamental processes that likely occurred when comets and asteroids in our early solar system first encountered the young sun's radiation. By studying these processes in real time around our interstellar visitor, astronomers can validate and refine theoretical models of early solar system evolution, gaining insights into the conditions that existed during the epoch of terrestrial planet formation. The isotopic ratios preserved in 3I Atlas provide a direct window into stellar nucleosynthesis processes that operated in the galaxy's past, revealing information about the types of stars that were living and dying when these materials first condensed from enriched interstellar gas and dust. different generations of stars have contributed different combinations of elements to the galactic chemical inventory, creating an evolutionary sequence that can be traced through the isotopic signatures of objects like our cosmic visitor. The specific ratios of oxygen, carbon, nitrogen, silicon, and other elements found in 3I Atlas tell us about the relative contributions of different stellar populations. Massive stars that ended their lives in spectacular supernova explosions. Intermediate mass stars that shed their outer layers as planetary nebulae, and the gradual neutron capture processes that occurred within the cores of long-lived red giant stars. This isotopic archaeology allows us to reconstruct the stellar genealogy of our local galactic environment with unprecedented detail. Perhaps most intriguingly, the organic chemistry preserved within 3I Atlas may represent a snapshot of prebiotic chemical evolution that occurred under conditions very different from those that prevailed during Earth's formation. The complex carbon compounds and potential biochemical precursors carried by our visitor underwent chemical development in a stellar environment that may have been more or less favorable for the emergence of life than the conditions that existed in our own primordial solar system. The temporal paradox extends beyond chemistry to our understanding of galactic dynamics and cosmic evolution. The trajectory and velocity of 3I Atlas carry encoded information about the gravitational environment it encountered during its interstellar journey, providing clues about the distribution of dark matter, the influence of spiral density waves, and the effects of stellar encounters over cosmic timescales. This kinematic information helps astronomers reconstruct the dynamical history of our local galactic neighborhood and make predictions about how it will continue to evolve as the Milky Way ages and eventually collides with the Andromeda Galaxy in approximately 4 billion years. Deep within the microscopic structure of 3I Atlas, at the most fundamental level of atomic and molecular organization, quantum mechanical processes are orchestrating an intricate symphony of interactions that reveals some of the most profound secrets of cosmic chemistry and the fundamental nature of matter itself. These quantum phenomena, operating on scales millions of times smaller than the width of a human hair, hold the key to understanding how complex molecular structures can not only survive but actually evolve and transform during the extraordinarily harsh journey between stellar systems across the frozen vacuum of interstellar space. The quantum mechanical properties of individual atoms within 3I Atlas determine every aspect of how they interact with their neighbors, creating the complex three-dimensional molecular architectures that serve as the fundamental building blocks of organic chemistry and potentially even primitive biological systems. Electron orbitals, the quantum mechanical probability distributions that describe the statistical likelihood of finding electrons in specific regions around atomic nuclei, overlap and interact in precisely defined ways that govern molecular geometry, chemical reactivity, thermodynamic stability, and the pathways through which chemical reactions can proceed. These quantum interactions are so fundamental that they control everything from the crystalline structure of mineral phases within our cosmic visitor to the folding patterns of complex organic polymers that may represent primitive steps toward biological organization. The quantum mechanical principle of electron spin pairing determines which atoms can form stable chemical bonds with each other, while the wave-like nature of electrons allows for phenomena like resonance stabilization that gives certain molecular structures enhanced stability over cosmic time scales. During 3I Atlas's million-year odyssey through interstellar space, continuous bombardment by cosmic rays has induced countless quantum mechanical transitions within the atoms and molecules composing the object's structure. High-energy particles striking atomic nuclei can promote electrons to higher energy states, break existing chemical bonds through electronic excitation, and create entirely new molecular configurations through processes that can only be understood through the sophisticated mathematical framework of quantum mechanics. Some of these radiation-induced changes have created exotic molecular species that may not exist anywhere else in our solar system, essentially transforming 3I Atlas into a unique cosmic laboratory for studying chemistry under extreme conditions. The cosmic ray environment of interstellar space provides a constant source of high-energy photons, electrons, protons, and heavier atomic nuclei that can initiate chemical reactions impossible to replicate in terrestrial laboratories, leading to the formation of unusual isomers, exotic molecular geometries, and potentially even entirely new classes of organic compounds. The quantum mechanical tunneling effect plays a crucial role in enabling the slow but continuous chemical evolution that occurs within 3I Atlas, even at the extremely low temperatures of interstellar space, where classical thermal energy is insufficient to drive most chemical reactions. Normally, chemical transformations require reactant molecules to possess enough kinetic energy to overcome activation barriers, the energy hills that separate stable molecular configurations from their reaction products. However, quantum mechanics allows particles to tunnel through these energy barriers, even when they lack the classical energy necessary to surmount them, enabling chemical reactions to proceed at measurable rates, even at temperatures just a few degrees above absolute zero. This quantum tunneling mechanism has allowed the organic chemistry within 3I Atlas to continue evolving throughout its interstellar journey, creating molecular diversity and complexity that would be impossible under purely classical physics. The magnetic properties observed in 3I Atlas emerge directly from quantum mechanical phenomena, particularly the intrinsic quantum mechanical property known as spin that characterizes both electrons and atomic nuclei. These quantum spins can be thought of as microscopic magnetic dipoles that interact with each other and with external magnetic fields in ways that create the complex magnetic field patterns detected around our interstellar visitor. The specific magnetic signature of 3I Atlas reflects the quantum mechanical ground states and excited states of countless atoms and molecules within its structure, providing detailed information about electronic configurations, chemical bonding environments, and the local symmetry of atomic arrangements that cannot be obtained through any other experimental technique. Advanced quantum mechanical calculations are required to interpret these magnetic signatures and extract meaningful information about the internal structure and composition of our cosmic visitor. Quantum mechanical coherence effects may also contribute to preserving the structural integrity of delicate molecular architectures within 3I Atlas over the cosmic timescales of its interstellar journey. Certain quantum states can exhibit remarkable stability and resistance to environmental perturbations, maintaining their characteristic properties for extraordinarily long periods when properly isolated from sources of decoherence. The near-perfect vacuum and ultra-low temperatures of interstellar space create nearly ideal conditions for maintaining quantum coherence in molecular systems, potentially allowing fragile quantum states to survive the journey between stellar systems with their essential properties intact. This quantum preservation mechanism may explain how complex organic molecules and potentially even primitive information storage systems could survive interstellar transport and contribute to the emergence of life when they encounter appropriate planetary environments. The interaction of electromagnetic radiation with matter within 3I Atlas is governed entirely by the quantized nature of energy transfer described by quantum mechanics. When photons from stellar sources interact with atoms and molecules in our cosmic visitor, they can only be absorbed or emitted in discrete energy packets corresponding to specific quantum mechanical transitions between allowed energy levels. This quantized interaction creates the characteristic spectroscopic signatures that allow astronomers to identify chemical species, determine physical conditions, and track chemical evolution within 3I Atlas. The precise wavelengths at which absorption and emission occur depend on the quantum mechanical energy level structure of individual atoms and molecules, creating unique fingerprints that reveal not only chemical composition, but also information about molecular geometry, vibrational states, and rotational motion. The arrival and comprehensive study of 3I Atlas represents far more than a remarkable astronomical event or scientific discovery. It embodies a fundamental transformation in humanity's philosophical relationship with the cosmos, challenging our deepest assumptions about isolation, uniqueness, cosmic purpose, and our place in the grand narrative of universal evolution. This interstellar messenger has initiated what may prove to be the most profound revolution in human consciousness, since the Copernican principle first displaced Earth from the center of the universe, forcing us to confront the reality that we exist not as isolated observers of distant phenomena, but as active participants in a vast interconnected galactic ecosystem. The philosophical implications begin with the most basic recognition that materials from other star systems can and do regularly visit our cosmic neighborhood, carrying with them the chemical and isotopic signatures of alien worlds. This simple but profound fact completely demolishes the conceptual barriers that have long separated our solar system from their distant stellar realms, revealing instead a universe where matter, energy, information, and potentially even the seeds of life itself flow freely between stellar systems over cosmic timescales like nutrients circulating through the organs of a vast cosmic organism. The traditional astronomical paradigm, developed over centuries of Earth-based observation, viewed star systems as discrete, isolated entities separated by vast gulfs of apparently empty space that seemed to prohibit any meaningful interaction or exchange. 3I Atlas demonstrates that this isolation is largely an illusion created by the limitations of human perception and the relatively brief timescales of human existence. We actually live in a galaxy where stellar systems are intimately connected through an ongoing exchange of materials that creates a kind of cosmic metabolism operating over billion-year time cycles. This revelation fundamentally alters our understanding of planetary formation, chemical evolution, and biological development throughout the galaxy. Rather than developing in complete isolation using only the materials available within our birth solar system, Earth and the life it supports have been continuously shaped and enriched by contributions from countless other stellar realms. The water in our oceans, the carbon in our bodies, the oxygen we breathe, the calcium in our bones. All of these fundamental components of terrestrial existence may have been enhanced and enriched by materials delivered by previous interstellar visitors similar to 3I Atlas over the billions of years since our planet first formed. We are revealed to be not merely products of our local stellar environment, but rather cosmic citizens whose very existence reflects the chemical contributions and evolutionary processes of stellar systems scattered throughout our corner of the Milky Way galaxy. Our biological heritage extends far beyond Earth's biosphere to encompass the nuclear furnaces of ancient stars, the shock waves of supernova explosions, and the slow circulation of enriched materials through the interstellar medium that has been operating since the first generations of stars began to synthesize heavy elements. The complex organic chemistry detected within 3I Atlas raises even more profound philosophical questions about the nature, distribution, and inevitability of life throughout the universe. If sophisticated carbon-based compounds can form naturally in other stellar systems, survive the million-year journey through interstellar space, and potentially contribute to biological processes when they encounter suitable planetary environments, then the fundamental building blocks of life are not unique to Earth, but represent a common thread woven throughout the fabric of galactic evolution. This suggests that life itself may be an inevitable consequence of cosmic chemistry and physics, rather than an extraordinarily rare accident confined to our single planet. The philosophical implications are staggering and transformative. Rather than being alone in a vast, sterile, and indifferent universe, we may be part of a galactic community of worlds where life emerges naturally wherever suitable conditions persist for sufficient time periods. The universe may be not only stranger than we imagine, but also far more alive and interconnected than our Earth-centric perspective has traditionally allowed us to consider. The temporal aspects of 3I Atlas's journey also challenge our conventional understanding of causation, influence, and connection across cosmic timescales that dwarf human comprehension. The materials we are studying today were shaped by stellar processes that occurred billions of years ago, in stellar environments that may no longer exist, around stars that may have already completed their evolutionary cycles and dispersed their constituent matter back into the interstellar medium. Yet these ancient materials are influencing our understanding, our technological development, and potentially our future evolutionary trajectory in the present moment. This temporal mixing and cross-connection suggests that the universe operates according to principles of interconnectedness that transcend our ordinary experience of linear time, sequential causation, and the apparent separation between past, present, and future events. The study of 3I Atlas is also revealing the fundamental limitations of our traditional scientific methodologies and forcing the development of entirely new approaches to understanding cosmic phenomena that exist at the intersection of multiple disciplines. Our interstellar visitor cannot be adequately understood through the lens of any single scientific specialty. It requires unprecedented synthesis and cooperation among astronomy, chemistry, physics, biology, geology, and even philosophy and consciousness studies. This interdisciplinary collaboration represents a new mode of scientific investigation that may prove essential for understanding the increasingly complex challenges facing humanity as we transition from a planetary to a potentially interplanetary and eventually interstellar civilization. The holistic, systems-thinking approach required to comprehend 3I Atlas provides a template for addressing global challenges such as climate change, resource depletion, and the long-term sustainability of technological civilization. Perhaps most profoundly, 3I Atlas serves as a tangible reminder of cosmic deep time, the almost incomprehensible spans of time over which cosmic evolution unfolds, and the humbling recognition that human civilization represents just the briefest moment in a story that began billions of years before our species existed and will continue for billions of years after our current form has evolved into something unrecognizable. The object's million-year journey between stars represents just the tiniest fraction of its overall history, which extends back through geological ages to the formation of materials around an ancient star that may have completed its life cycle before our sun even began to condense from the interstellar medium. This temporal perspective places all of human history, all of our cultural achievements, all of our scientific discoveries, and all of our future aspirations within a cosmic context that is simultaneously humbling and inspiring. The comprehensive study of 3I Atlas has catalyzed an unprecedented technological revolution in astronomical instrumentation, data analysis methodologies, and space exploration capabilities, pushing the boundaries of human engineering ingenuity to their absolute limits and creating entirely new scientific disciplines that will define the future of cosmic exploration for generations to come. This technological genesis extends far beyond simple improvements in telescope design or detector sensitivity. It represents a fundamental transformation in how we approach the investigation of cosmic phenomena, requiring innovations that span everything from quantum sensors capable of detecting individual photons to artificial intelligence systems that can process and interpret vast streams of multidimensional data in real time. The observational challenges presented by 3I Atlas have driven the development of adaptive optics systems of extraordinary sophistication that represent pinnacles of precision engineering and real-time control theory. These technological marvels employ deformable mirrors controlled by hundreds or even thousands of individual actuators that can reshape the mirror surface thousands of times per second, guided by laser guide star systems that probe atmospheric turbulence conditions in real time using artificial beacons created by powerful lasers tuned to excite sodium atoms in the upper atmosphere. For studying the subtle details of 3I Atlas's surface composition and internal structure, these adaptive optic systems have been pushed to their absolute theoretical limits, achieving angular resolutions that approach the fundamental diffraction limit imposed by the wave nature of light itself. The technological advances developed specifically for 3I Atlas observations, including predictive control algorithms, ultra-fast wavefront sensors, and next-generation deformable mirror technologies, are already revolutionizing our ability to study exoplanets orbiting nearby stars, resolve surface features on distant stellar companions, and detect the gravitational lensing effects of dark matter concentrations throughout the galaxy. The spectroscopic analysis of 3I Atlas has necessitated the development of revolutionary new spectrometer designs with unprecedented wavelength coverage, spectral resolution, and photon detection sensitivity. Modern instruments designed specifically for interstellar object research can simultaneously observe across enormous spectral ranges spanning from the far ultraviolet through the near infrared, covering wavelength ranges that encompass more than 4 orders of magnitude, while maintaining the spectral resolution necessary to detect subtle isotopic signatures and trace molecular species present in concentrations of just a few parts per billion. These instruments employ cutting-edge detector technologies, including superconducting tunnel junction devices cooled to temperatures just above absolute zero, transition edge sensors that can detect individual photons and determine their energy with extraordinary precision, and kinetic inductance detectors that combine the sensitivity of superconducting devices with the practicality of semiconductor fabrication techniques. The data processing pipelines required to handle the enormous volumes of spectroscopic information generated by these instruments have driven parallel advances in machine learning algorithms, quantum computing applications, and distributed processing architectures specifically optimized for astronomical data analysis. Perhaps most remarkably, the study of 3I Atlas has accelerated the development and deployment of space-based interferometry systems that represent some of the most challenging engineering achievements in the history of space exploration. These distributed telescope arrays combine light collected by multiple spacecraft flying in precise formation to create virtual telescopes with effective baseline lengths measured in thousands or even tens of thousands of kilometers, achieving angular resolutions equivalent to optical telescopes with mirrors the size of entire continents. The technical challenges involved in maintaining precise formation flying among multiple spacecraft, coordinating their observations to within nanosecond timing precision, correcting for the effects of gravitational perturbations and thermal distortions, and coherently combining their signals to create high-resolution images represent unprecedented achievements in spacecraft engineering, quantum metrology, and precision control systems. The interferometric observations of 3I Atlas have resolved surface features and compositional variations that would be completely impossible to detect using conventional single-dish telescopes, providing detailed maps of our interstellar visitors' geology and revealing the complex history recorded in its surface materials. The magnetic field measurements required to understand the electromagnetic properties of 3I Atlas have driven the development of magnetometers so sensitive they can detect field variations smaller than Earth's magnetic field by factors of millions or even billions. These quantum sensors employ superconducting quantum interference devices, SQUIDs, operating at temperatures just above absolute zero, combined with sophisticated magnetic shielding systems and vibration isolation platforms that eliminate external interference sources. The most advanced systems can detect magnetic field changes equivalent to those that would be produced by a single electron spin located several meters away from the sensor, providing unprecedented sensitivity to the subtle magnetic signatures that reveal information about the internal structure, composition, and evolutionary history of cosmic objects. Deploying such exquisitely sensitive instruments in the harsh environment of space requires extraordinary attention to electromagnetic compatibility, thermal stability, and mechanical isolation, leading to innovations in spacecraft design that minimize magnetic contamination and mechanical disturbances. The gravitational field mapping of 3I Atlas has pushed precision timing, ranging, and navigation technologies to the very limits imposed by the fundamental laws of physics. Laser interferometry systems originally developed for gravitational wave detection have been adapted and enhanced to measure minute changes in spacecraft trajectories as they execute flyby maneuvers past our interstellar visitor, requiring timing precision measured in attoseconds, billions of seconds, and distance measurements accurate to fractions of the width of atomic nuclei. These measurements represent a marriage of Einstein's general relativity theory, quantum mechanics, and precision engineering that approaches the theoretical limits imposed by the uncertainty principle and the discrete nature of space-time at the smallest scales. The technology development has required advances in laser stabilization, frequency metrology, and quantum-enhanced measurement techniques that are finding applications throughout precision physics and may eventually contribute to the development of practical quantum computers and communication systems. The analysis of complex organic compounds within 3I Atlas has driven revolutionary advances in mass spectrometry and molecular analysis techniques that can identify individual molecules present in concentrations approaching the fundamental limit of single-molecule detection. These analytical instruments employ multiple stages of ion selection, fragmentation, and mass analysis, combined with novel ionization techniques that can gently transfer large organic molecules from solid surfaces into the gas phase without destroying their delicate chemical structures. When combined with advanced gas chromatography systems capable of separating complex molecular mixtures into their component compounds, and coupled with quantum mechanical modeling techniques that predict the behavior of molecular ions under various analytical conditions. These systems provide detailed chemical fingerprints that reveal not only the molecular composition of samples, but also their three-dimensional structure, isotopic makeup, and potential formation pathways. The techniques developed for 3I Atlas are already being applied to the search for biosignatures in samples returned from Mars and other planetary bodies, and will be essential for analyzing materials collected by future interstellar probe missions. As our gentle journey through the scientific, philosophical, and technological landscape illuminated by 3I Atlas draws to its peaceful conclusion, we find ourselves forever transformed by this profound encounter with a messenger from the depths of interstellar space. Like ripples spreading outward in ever-widening circles from a stone cast into the still waters of a mountain lake, the influence of this cosmic visitor will continue to propagate through human consciousness, scientific understanding, and technological capability long after the object itself has faded beyond the detection limits of our most powerful instruments and returned to the cosmic darkness from which it so gracefully emerged. The story of 3I Atlas is ultimately a story about the fundamental interconnectedness of all things, connection across the seemingly impossible vastness of interstellar space, connection across the almost incomprehensible spans of cosmic time, connection across the apparent gulfs that separate one stellar system from another, and most importantly, connection between the cosmic processes that shape the universe and the emergence of consciousness that allows the universe to contemplate itself. This interstellar messenger has demonstrated with quiet eloquence that the barriers we perceive between different regions of space and time are not fundamental features of reality, but rather limitations imposed by our necessarily limited perspective as creatures who experience existence on planetary scales and biological timescales. The materials that compose 3I Atlas, the pristine water ice that condensed in the frigid outer regions of an ancient stellar system, when the galaxy was young, the complex organic compounds that underwent patient chemical evolution during a million-year journey through the near-perfect vacuum of interstellar space, the minute mineral grains that preserve within their crystalline structures the magnetic memories of stellar winds that blew billions of years before our sun began to shine. All of these substances carry within their atomic and molecular architecture the indelible fingerprints of cosmic processes that shaped our corner of the Milky Way galaxy, long before our solar system existed. By studying these materials with instruments of unprecedented sensitivity and analytical power, we have gained direct access to the deep history of our galactic neighborhood, touching and analyzing samples of matter that witnessed the birth and death of massive stars, the formation and destruction of entire planetary systems, and the slow but inexorable chemical enrichment of the interstellar medium with the heavy elements necessary for rocky worlds and carbon-based life. We have become cosmic archaeologists, excavating the history of stellar evolution written in the isotopic ratios and molecular structures of an object that has traveled farther and endured longer than any human artifact ever will. The sophisticated organic compounds detected within 3I Atlas have revealed that the chemistry of life extends far beyond the boundaries of our solar system, existing naturally in the vast spaces between stars and potentially seeding new worlds with the molecular building blocks necessary for biological evolution. Complex carbon-based molecules, amino acid precursors, nucleotide bases, and even primitive membrane-forming compounds exist as common features of the galactic chemical inventory, suggesting that life may be not an extraordinary accident confined to Earth, but rather a natural and perhaps inevitable expression of cosmic chemistry that emerges wherever suitable conditions persist for sufficient periods of time. This revelation transforms our understanding of our place in the universe from that of isolated biological anomalies to representatives of a phenomenon that may be as common and natural as the formation of stars themselves. We are revealed to be participants in a cosmic evolutionary process that operates on scales vastly larger and timescales vastly longer than human civilization, but which achieves its most remarkable expression in the emergence of consciousness capable of understanding and appreciating the magnificent complexity of the universe that gave it birth. The technological innovations driven by 3I Atlas research have created scientific capabilities that seemed like pure science fiction just decades ago. Quantum sensors that can detect individual photons and measure magnetic fields smaller than those generated by single atoms. Space-based interferometers that combine light from multiple spacecraft to achieve angular resolutions equivalent to continental-sized telescopes. Analytical instruments that can identify and characterize individual molecules in samples smaller than grains of dust, and artificial intelligence systems that can process and interpret astronomical data streams containing more information than all of human literature combined. These technological advances will enable future generations of astronomers and explorers to detect and study other interstellar visitors with unprecedented detail, search for signs of life around nearby stars with sensitivity approaching the theoretical limits imposed by physics, and eventually launch robotic probes that will venture beyond our solar system to directly explore the stellar neighbors from which objects like 3I Atlas originate. We stand at the threshold of becoming an interstellar species, capable of direct exploration and communication across the vast distances that separate stellar systems. The gravitational and electromagnetic effects of 3I Atlas, though so subtle they require the most sophisticated instruments ever built to detect, have provided new and increasingly precise tests of our understanding of fundamental physics, opening windows into the nature of space-time, quantum mechanics, dark matter, and the invisible forces that govern cosmic evolution on the largest scales. These investigations have revealed that even the smallest cosmic objects can serve as natural laboratories for exploring the most profound questions about the nature of reality itself, connecting the physics of elementary particles to the structure and evolution of the universe as a whole. Perhaps most importantly for the future of human civilization, 3I Atlas has served as a catalyst for unprecedented international cooperation in scientific research that transcends national boundaries, cultural differences, and political divisions in service of our common quest to understand the cosmos and our place within it. The comprehensive study of this interstellar visitor has required coordination among telescopes, research institutions, space agencies, and scientific communities scattered across every continent, creating collaborative networks and communication protocols that provide a template for how humanity might approach the even greater challenges that await us as we venture beyond our home planet and take our first tentative steps into the broader galactic community. The philosophical transformation initiated by our encounter with 3I Atlas extends to our understanding of time, causation, purpose, and cosmic evolution itself. This ancient traveler has carried materials shaped by stellar processes that occurred in the distant past directly into our present moment, demonstrating that the universe operates according to principles of connection and continuity that transcend our ordinary experience of linear time and sequential events. The past, present, and future of cosmic evolution are intimately connected through the circulation of matter, energy, and information between stellar systems, making us simultaneously products of ancient cosmic processes and participants in evolutionary developments that will shape the galaxy for billions of years to come. As 3I Atlas continues its graceful journey toward the outer reaches of our solar system and eventually returns to the interstellar medium from which it came, it will carry with it subtle but permanent alterations in its chemistry, structure, and electromagnetic signature that record its passage through our cosmic neighborhood. Future civilizations that encounter this wandering messenger millions of years hence will find within its materials evidence of our sun, our planets, the composition of our interplanetary environment, and perhaps even molecular traces of the biological processes that have shaped Earth's biosphere during the brief moment when human civilization flourished on our small blue world. In this way, 3i Atlas serves not only as a messenger bringing us news from distant stellar realms, but also as an ambassador that will carry information about our solar system, our planet, and potentially even our species to future encounters with other forms of consciousness that may arise elsewhere in the galaxy. We are connected to the cosmic community not only as recipients of messages from afar, but as contributors to the ongoing conversation between intelligent beings separated by vast distances of space and time. The eternal echo of our encounter with 3i Atlas will reverberate through human consciousness and cosmic understanding for as long as our species endures, influencing our scientific methodologies, technological capabilities, philosophical perspectives, and understanding of our cosmic destiny. This remarkable interstellar messenger has shown us that we are not alone in the universe, not because we have detected radio signals from alien civilizations or discovered fossilized microbes in ancient meteorites, but because we have learned that we are integral components of a vast, interconnected galactic ecosystem where the materials, chemistry, energy, and perhaps even the seeds of consciousness itself flow continuously between stellar systems in an endless dance of cosmic connection and mutual influence. As consciousness gently dissolves into the peaceful realm of sleep, carried along by the same cosmic currents that brought 3i Atlas to our solar system, we can rest in the profound knowledge that we are not isolated specks of matter and awareness adrift in an indifferent universe, but rather cherished components of a magnificent, interconnected cosmic organism whose story continues to unfold through our observations, discoveries, dreams, and the endless human quest to understand our place in the infinite mystery of existence. The message of 3i Atlas is ultimately a message of hope, wonder, belonging, and profound connection, a gentle reminder that in studying the cosmos, we are not merely learning about distant phenomena, but rather discovering the deepest truths about ourselves and our eternal place in the magnificent, ever-evolving tapestry of cosmic consciousness.